For decades, computers processed human language without understanding a word of it. They could search and sort text, but the logic behind the sentences remained opaque. Today, artificial intelligence has shifted from matching keywords to modeling the complex relationships between them. This shift required engineers to solve a historical roadblock known as algorithmic amnesia. Older neural networks process data strictly sequentially. They evaluated sentences left to right, analyzing a single word, storing its limited context, and then moving to the next. If you feed these systems a scenario about a ship's captain navigating a storm to deliver a vital payload, the bottleneck fails. By the time it reaches the word payload, the captain from the beginning has been forgotten. Engineers realized that throwing more raw computing power at a linear bottleneck yielded diminishing returns. To achieve comprehension, the industry required an architecture capable of viewing and processing an entire block of text simultaneously. Human thought does not exist as a string of isolated fragments. True comprehension requires seeing the total context of an idea all at once. Consider a complex input. The architect realized the foundation was compromised only after the catastrophic sensor silence. The machine's first mechanical step is tokenization. It takes our human sentence and shatters it into discrete foundational fragments. Computers do not process English. To interpret these fragments, the system uses vector embeddings, translating each token into a multidimensional numerical array. These arrays act as coordinates, plotting the tokens into a vast mathematical space. Words with similar meanings, like architect and foundation, physically cluster together based on their numerical properties. But looking at all these clustered words at once introduces a flaw. Without linear reading, the original sequence of the human sentence is destroyed. To solve this, the architecture applies positional encoding. It stamps a mathematical timestamp onto each token. This locks in the chronological order of the words while preserving their new spatial relationships. The machine has now stripped away the linear nature of human language, successfully converting a complex prompt into a precise, navigable mathematical space. With the map built, the architecture activates its core engine, multi-headed attention. The attention mechanism deploys multiple processing heads to scan the mathematical space simultaneously. One head analyzes the specific relationship between the architect and the foundation, while another links the sensors to the silence. Older systems guessed meaning based on whichever word was adjacent. Here, meaning is derived from these interconnected relationships, viewing the entire sentence as a single, unified structure. Once this web of context is fully encoded, the data is handed over to the decoder architecture to generate a response. The decoder utilizes an auto-regressive generation loop. It calculates the most logical next token, then loops that newly generated word back into its own input stream, running the entire process again to find the word after that. Because every new word alters the context of the entire web, the machine reevaluates the full structure every cycle. It is actively synthesizing a novel, contextualized thought. Zooming out from a single sentence to the industry scale, these processes are stacked across dozens of layers. When a model has billions of parameters, it refers to the billions of learned relational weights stored within the structure. In modern deployment, the encoders, the part of the system learning the general rules of the world, are often pre-trained on massive datasets and then permanently locked or frozen. This static knowledge base feeds into dynamic decoders fine-tuned for specific tasks. To prevent memorizing training data, dropout layers randomly disable internal nodes. The machine must constantly reroute its pathways, ensuring it learns core concepts instead of just cheating the test. This architecture maps data into structures that exist regardless of the medium. It is a system built to identify patterns in any high-dimensional space. Researchers now use this relational map to decode overlapping audio waves, process pixels and visual media, and sequence the complex structures of biology. By encoding these relational weights, we have built a mathematical engine that can predict the next logical step in any complex system. We have scaled the architecture of context into a tool that mirrors the way information is structured throughout the world.